lengthy as I just did. Just had a question on differential equations, if that was adjustable in any way, shape, or form. What I would suggest to anyone who's wanting to sign up for it, please sign up for it so the course will have a better chance of making. The question was, the timing is just absolutely terrible for one student, but I said go on and sign up for it, and then usually the instructor will work with you on that. So if you are contemplating differential equations, linear algebra, well, let's see, this is Cal 3, one of your physics courses, please sign up. They may start canceling classes. I don't know when, but probably not until January, but they may actually start sooner. So please sign up for what you want to take. Now, even if the timing's not great or anything else, then work with the instructor. And right now, the instructor for differential equation, as Kyle said, was TBA, to be announced. It's not going to be me. I usually teach it, but we'll see if we can get someone in place by next term. So go on and sign up. Otherwise, they'll cancel the class. So please sign up for whatever you want to take sooner rather than later. Okay. Now, any other questions, issues, concerns, problems? Let me just make sure nobody else is in the wings here. I just see 2 students so far. Yep, Kira and Kyle. I keep trying to mix those 2 names up. So let's go on and set up for where we left off last time. Any other questions before we get going? Okay, let me hit a few other things before we get going. This, by the way, speaking of which, when Kyle was talking, is probably my last Cal 3 class to teach, period, okay? Because next week is final exams. I'll be here. If you need me, I'll be here, but I won't be setting up a Zoom for this class. So if you need me, email me, get in touch with me some way or another, and Blackboard message somehow, and we can set up to answer questions or do. Now, maybe I should phrase it this way. Do y'all think you would want to have a Zoom set up for either Monday or Wednesday of next week, just in case you have questions? Or do you want to just get in touch with me some other way? Anybody? Either of you?
It won't be no point for you to set up Zoom because don't nobody be here.
Right. Okay. So if you need to get in touch with me, email me, message me on Blackboard messages, or if you got my number, call my number. I will be here. I don't go anywhere. I'm not going anywhere, not with COVID out there. The only place I might be is at the Kirkland Clinic, having another blood draw or something like that. But I usually try to go in as early as I can in the morning before any more people get there, and then I can get in, get out, and be minimal exposure. Okay, but except for that, I'm here. I am here. So just email me or send me a message on Blackboard Messenger, or if you have my number, you can call. That's perfectly fine too. Okay, please do the student course evaluations. They finally got them open. I don't know if it's the week before Thanksgiving or the week of Thanksgiving, but it was awfully late for them to open them, but they do have them open now. So please do the student course evaluations. Now, if either of you were in and here comes James, let me get him in here, and I'll hold off my next thought until he gets in. So James is here. 3 out of 8 present and accounted for. Okay. And So the top part of the alphabet's here, the middle part of the alphabet's here, but nobody's here from the bottom. So hopefully they'll be coming in. James, can you hear me yet?
Yes, sir.
Okay, good deal. I was just talking about student course evaluations. They finally got them open. If any of you were in a first mini-term course, you did not get to, oh, wait a minute, here's your manual. Okay. So now the bottom half of the alphabet is caught up with the top half, and it's a dead heat tie here. Okay. Or the other way to look at it, poor old Kira is holding up the top part by herself. The middle part is really strong with 3 and nobody at the bottom. So, oh, and here's Laron. Talk about the bottom of the alphabet. He's here now. Okay. So we have a fairly symmetric grouping here, not quite, a little off, skewed to the bottom, but 1 at the top, 1 at the bottom, and 3 in the middle. So, way to go. Glad y'all are here. Jemanuel, can you hear me yet? I take it you can. I hear you, I believe, but you may not realize that your microphone's on. Okay. And let me see if Laron has made it in yet or not. Laron, can you hear me?
Yes, sir, I can.
Good deal. Okay. All right. So we've got 5 out of 8 here. I was just going over how we're going to end the term, kinda, okay? And the first thing I was saying, okay, number 1, this came up earlier, so since y'all may not go back and listen to the YouTube video, you may miss it. But the question was, is there any flexibility on the timing? This isn't quite the question, but pretty close to it, on the timing of, say, a differential equations course or something else. And my advice to the questioner was register for it, because we are, I think we just lost somebody, didn't we? Kyle, no, Kyle's still here. I think it was James. Hopefully he'll be back. Okay. But go on and register for the courses you need, and then work with the instructor to see about adjusting times or something. It may be, some of these classes may be taught as independent studies or things like that. I don't know how they're going to run them. I've always taught them whether I got paid for them or not. We can't ask anybody else to do that. So they may teach as independent study or something on that line. So go on and sign up for your classes. Don't hesitate. Get it out there, because when January gets here, maybe even beforehand, but when January gets here, they will start slashing and burning like they always do, canceling classes, cutting them, and stuff like this. When I was the instructor, I think they knew better than to do too many of those cancellations, because I was going to raise a fit. But I'm not going to be the instructor anymore, so there's no one there to raise a fit. So please sign up for your classes. Okay, that's one thing. Number 2, they finally opened student course evaluations. Now, this was either the week before Thanksgiving or the week of Thanksgiving. I can't remember which. The problem was, of course, Banner, this operating system that we now work under. They were having enormous problems getting them to communicate. The screen Smart Eval is the name of the package that we've always used. I don't think there'll be any change there, but how you get in and that kind of stuff. Check your emails. Please do the student course evaluations. They're very, very important. Okay, if any of you were in a first mini-term class, please go back and do the first mini-term evaluations as well, because they could not, from what I understand, get this to work before now. So they did not have these available for first mini-term students. Okay, that said, what we're going to do today is, this, by the way, is my last Calculus 3 class that I may teach. I don't know for sure, but my guess is that. Okay, so what the ramifications are there, we're not meeting again. I will be available. Email me or send me a Blackboard message, either one of those, and I will probably see it. If you have my phone number, call me. That will work too. Okay, but better email or Blackboard message. Okay, I'll be here. I don't go. I do have early next week to go to Kirkland Clinic and have another blood draw. They're monitoring my anemia pretty closely now, once a week so far. So I think that'll still continue for a while. But except for that, I'll be here. I don't think they're planning any procedures or anything else. They're just monitoring the anemia, which I still am anemic, but it's nowhere close to critical anymore. So that has everybody a sigh of relief. So what will we do at the end of class today? I will try to show you the exam, and we'll go over if any of the questions need to be skipped or whatever. I won't be able to post it necessarily because it's probably in WordPerfect format. I'll have to go downstairs and do a Adobe scan on it and get it into PDF format so you can read it. So it'll probably be after 4 o'clock today before I actually post the last test. It'll be the Chapter 12 test. That's all that will be on it, Chapter 12. Okay, it may be that we don't get everything in Chapter 12 done, so it may be fewer than 10 questions. Boo hiss. I know you're sorry to hear that. Okay, any questions for me then? For those who may have come in later, please do the student course evaluations. All right. Okay, James hasn't made it back yet. Hopefully he will. I'll be watching for him. Now, we are in Chapter 12, Vector Value Functions. 12.3 is velocity and acceleration. We're almost through with that. We're in the very last part of Example 5 on the bottom of page 840. We got one more example to do, and we'll be on into 12.4. Okay, so we've already done this part of Example 5. And I'm trying to scroll through it and it won't scroll. Okay, any questions for me while I'm trying to bring this up? Okay. We got this far last time. Okay, this is the final part of Example 5, and this is where we left off. We started with a projectile with an initial position, initial velocity, find the position vector. This is the position vector. What we did was integrated both of those using the initial position vector and the initial velocity vector. Here's the initial position, there's the initial velocity, and by integrating twice, we got to this point right here. So there's your position vector as a function of time. Okay, this represents the acceleration, always pointed downward. That's why it's a negative j. And then this is your initial velocity times your time t. This is the initial acceleration is the 1/2 gt squared. Okay, negative 1/2 gt squared times time squared in the negative j direction. And then your initial velocity, whatever components it had in x or y direction, I or j direction, they're still there, multiplied by t. And then your initial position vector in the xy plane also is there. Okay, so there was our solution. Now, they'd go another step with this. Okay, the first part here is perfectly fine the way it's sitting now. Let me see. I don't need to, but I'm going to recharge my phone. We were doing some calculations in the last class. So it's not bad, but I just want to keep it charged. Okay. Okay. This is about as far as we can go. Minus 1/2 gt squared in the j direction. Okay. Now, that initial velocity, remember the initial velocity was something like, ooh, that's supposed to be horizontal, and this was supposed to be your projection. Better than that, should be a parabola. And here was your initial velocity in this direction, v0. Well, that has an I component and a j component. There would be the I component, there would be the j component. The I component, if you know this angle here, theta, the I component here would be the cosine of theta. So this would be plus v0 times the cosine of that angle theta, initial angle theta, and that's in the I direction, and the j direction would be the sine of that. So that would be plus, oh, here's James back. Good deal. Glad he made it back. All right, James, in case you can hear me now, we're in on page 840, chapter 12, vector value functions, 12.3, velocity and acceleration, bottom of page 840, finishing, wrapping up, example 5. Okay, and what we're doing with it is, here was your acceleration here, only in the j direction. Your initial velocity of your projectile would be some part in the I direction, and that would depend on the cosine of that angle theta, and in the j direction would depend on the sine. So that would be v0 times the sine of theta naught. Did they call it theta naught or theta? I think they just called it theta. Yeah, theta. In the I direction. Okay. Now, your position vector, I believe their picture was, it was just h in the j direction. So that is just h in the j direction. Okay. All right. That is whatever the initial height was. Okay. I didn't draw mine very well. They had it starting from up here with the initial height h. Okay. So if you combine the values together, and this was j here, I wrote I. Okay, if you combine the things together, you only have one component in the I direction, and that's your initial velocity times the cosine of theta, and that's always there. So it's v0 cosine theta I, okay, plus, and then in the j direction, doesn't matter which order you do it. I kind of don't like starting with the minus sign, but I will. Minus 1/2 gt squared plus, oops, y'all let me get away with that. There's a t in there, t times initial velocity. There's a t in there, and there's a t in there. There's no t in the displacement vector. It's not, okay? Plus v0 sine theta t plus h, all that in the j direction, and there you have it. Okay, one component in the I direction, and that's from your velocity moving you forward that way. Okay, depends on t. Three components in your that's probably not the worst, or three terms in your j component, then acceleration term, an initial velocity term, and your initial displacement term, because your initial displacement was only up. And that's what they've got here. And they did turn it around like I was wanting to do, but I thought they wouldn't do it. And they wrote the h first plus v0 sine theta t minus 1/2 gt squared j. That's how they wrote the last. Only one component in the I direction. Okay. Doesn't matter what order you write it. But anyway, there we have it. Now they did put their V0 sine theta in parentheses as they did the V0 cosine theta. That helps keep those things separated a little bit. Actually, they put V0 sine theta there, not there. Okay. Yeah. All right. That is a G. I think you can tell that. So they made this a bracket rather than a parentheses, so you wouldn't. Okay. That's it. Now, any questions on example 5? Took us a while to finish it, but we got it done. Okay. Now, here's that picture again. In many projectile problems, the constant vectors R0 and V0 are not given explicitly. Often you'll be given an initial height h, this is what I was just doing, an initial velocity V0, and the angle. This, okay, I should have shown this first, okay, at which the projectile was launched. Okay, so this is it, showing your R0 is a vertical displacement here. Okay, your initial velocity then takes off from there with an x component and a y component, I and j components, and then your acceleration you don't see anywhere, it's always downward. Okay, so with that in mind, then what we just did, and here it is. Okay, sorry about this. I wish I'd have moved the slide. I wouldn't have had to write it off for you. From the given height, you can deduce that the initial displacement vector was just hj, positive hj, up there. Okay, your velocity vector was xi plus yj, where x was, I didn't put the magnitude bars around it because I didn't put a vector over it. I just put V0, meaning the magnitude of V0 times the cosine of theta. Where in the world is my, there it is, times the cosine of theta I plus the magnitude of V0 times your sine theta j, and then they did the same thing, taking away the bold and just writing the it in regular type. That may even be italicized. I can't tell with a V whether that's italicized or not, but that's your initial velocity, the magnitude of the initial velocity. The cosine of it is the horizontal component, and the sine of that angle times that is your vertical component, just like we drew before. Okay, now, so that position vector can then be written, and this is what I did on the last slide. Leave this term alone, that's by itself. This will be t times your V0 cosine theta I plus t times V0 cosine theta t. Now, whether you put the variable in front or behind, it really doesn't matter. Okay, and then your R0 is just hj. Then combine your i's. There is only one I. T, and now here they wrote the t in front, here they write the t behind. Why they moved it, I don't know. But your coefficient is V0 cosine theta, that's just a number, times your variable t, I, and then your displacement part, h, plus V0 cosine theta t, that's your initial velocity vertically, times t, plus or minus 1/2 gt squared. Those are all your j components here, here, and there, and that gives you your overall displacement vector, broken down just about as far as you can break it. Okay? Now, here's top of page 841, theorem 12.3. Okay? Now, I think part of this is my anemia, and part of it may be, well, part of it is the fact that the sun has gone to the south side of the house and no longer coming in this east window, and I'm on the north side, so I don't get any sun at all from this side either. So it's getting a little chillier in here. I think I'll wait a minute because I know the cleaning lady's still out there working, so I don't want to bother her any. So in a few minutes I will, because my hands are so cold, and I never had cold hands before I had this anemia, so I'm blaming it on that. Position vector for a projectile, neglecting the air resistance. The path of a projectile launched from an initial height h with an initial speed v0 and the angle of elevation for that initial launch, meaning your velocity, is theta, is described by this vector function that we just had. The only piece of it is your velocity vector. The velocity vector in the direction, the horizontal direction. And that's v0 cosine theta t. Okay? Now, in the vertical direction, since it was initial height h, so that's only in the vertical direction, that would be h plus your component of your velocity vector, v0 sine theta t, okay, because sine is the opposite side. Well, we went on to baseball. Okay. The computer has been jumping around like this all day today. I don't know why it's so sensitive, but it seems to be. Okay. And then finally the acceleration component is minus 1/2 gt squared, and that's also only in the vertical direction, but vertically downward. Initial velocity is upward. Now if you got that baseball player to hit a ground ball, it went down. Okay, so that would have been down too. But if that was a fly ball, it went up. Okay. G is the acceleration due to gravity. That's the only component of acceleration. Okay. So here's example 6, the one that Kyle's been waiting for. See if he can make it over the fence here. A baseball is hit 3 feet above the ground. That's about right, isn't it, Kyle? That's a sweet spot right about belt level, right?
Yes, sir.
Okay, 3 feet above the ground, so that's your initial height, initial displacement vector, r0, 3 feet above the ground, and he hits it at 100 feet per second, okay, at an angle of 45 degrees. Now, that's a pretty smart angle to use because will give you the maximum range, okay? It says find the maximum height reached by the baseball. That's the first question. And the second question is, will it clear a 10-foot high fence located 300 feet from home plate? Okay, and this is obviously not drawn to scale, but it's drawn better than I could have. Okay, so basically what we have here is a lot like we were just describing before. Now, I don't know if I've got enough room to write here, but I'm going to try to get it done. Your displacement vector here, r as a function of time, is going to be your I component will be the initial velocity, 100 feet per second times the cosine of 45 degrees. Well, we know what the cosine of 45 degrees is. It's square root of 2 over 2. So that would be 50 root 2. And that is your I component of your motion, r of t. Now, how I got that, 100 times root 2 over 2. Cosine of 45 root 2 over 2. The 2 goes into 150 times, and you still have the root 2 in the numerator. Okay, plus, now, initial height, 3 feet. Okay, oops, you let me do it again, didn't you? This is times t. Okay, initial velocity always is multiplied by t. Okay, the 3 is not multiplied by t because that's just initial height. There's no time dependence of your initial height whatsoever. Now your initial velocity, that was again V0, 100. This is V0 here. Goodness gracious. This pen's been doing this stuff all day too. It will write sometimes and other times it won't. This is your theta 0 or theta. Okay, I'm going to call it theta 0 initial thing. Now this will be something out there. We'll worry about those later. All right. Now 3 plus V0 times the sine of 45. Well, sine of 45 is same as cosine 45 because that's your bisecting angle. Okay, so this will also be 50 root 2. 50 root 2 times t. Okay, this will be in the j direction. Minus 1/2 g. Now we're in feet per second, so therefore we're going to use 32 feet per second squared. That's acceleration due to gravity in the U.S. customary system. Okay, I didn't put units down on the others, but I did it here just so you'll recognize that as g. Then it'll be t squared, and all that is in the j direction. Okay, so that's your formula. Now I'm going to simplify this a little bit because I don't have much room. Half of 32 is 16. So I'm going to, if I can get the thing to come, oh it did. The last class I could not get that thing up there at one time. Okay, so I'm going to leave off the units too, make that 1/2 of 32 minus 16. I mean plus 16. I don't know where that minus sign came from. Plus 16. Oh, no, I know. Okay, I'm sorry. This is your vertical. This is your acceleration. That is a minus sign. Okay, duh. Okay, minus 16. 1/2. Okay. Now again, the old gray cells aren't working too well today. The t squared is in here. Where in the world? There it is. Okay. The t squared's in here, not out there. Okay. I think I had a parenthesis around everything else, and now I lost that parenthesis. So that's what we've got. Okay. Now, find the maximum height reached by the baseball. This I component has nothing to do with the height. So the maximum height reached by the baseball is from here. This is the height at any time t, so the maximum height would be, take a derivative, and that would be 50 root 2 minus 32t. Okay? All right. All right. Now, when that is equal to 0, because you're okay. Yeah, that's your vertical component, and when it stops increasing and starts decreasing, it's changing by that. First derivative is 0. Let's see what we got. T is equal to 50 root 2 over 32, and this will be 25 over 16. Okay, now I think I will need my calculator. Actually, my phone, which is using as a calculator. Okay. Let's see, that's 25 divided by 16 times square root of 2. I'm going to have to turn my calculator, my phone sideways to do times 2 square root equal. I get 2.2 seconds into its flight. Okay, so what is the displacement 2.2 seconds in? Well, I'll take that number, and its vertical component will be this one right here. So I'm going to first square that number. Let me go back sideways again. Okay, I'm going to square that, multiply it by 16, negate that, add to that 50 times root 2, okay, times that 2.2 seconds, and add to that 3. So the maximum height appears to be right around 40. Let's see if that's what they got. I mean 80, I've said 40. 80. Now they rounded somewhere along the way. It appears anyway. Or maybe I rounded. Oh no, they rounded up and made it 2.21 seconds. I left it in there, and so anyway, right around 80 or 81 feet. Okay, that's what we've got. Okay, now that answers the question, and this, by the way, is that question is approximately 80 to 81 feet. That's the maximum height. So even in the Superdome, it doesn't hit the ceiling. Okay, good. Okay, the question now, will it clear a 10-foot high fence located 300 feet from home plate? Well, 300 feet from home plate is your X value. Okay, that's how far you are from home plate. Well, that's measured by this. So when X is equal to 50 root 2 t. Let's find out what the t is. Oh, and this X is 300 feet, right? So let's divide out the 50 and the 300. That would give us 6 is equal to root 2 t. So divide both sides by root 2. And that should give you your time to reach the fence. Now we don't know that it'll get there, but if it does get there, it's going to be that many seconds. So let's do 6 divided by square root of 2 equal. Looks like about 4.24 seconds to get there. So the t to reach the fence, if I could get my pen to show up, t to the fence is about 2.42 seconds. I'm sorry, I say it backwards. 4.24 seconds. Okay? Now, let's take that and plug it in here and see if we're going to exceed the 10 feet. So, we'll take our vertical component here. 3, well, I'm just going to plug it in. The 4.24, first thing I'm going to do is square it. Okay, so I got to turn it sideways to do that. So square that. Wow. Okay. Multiply it by 16 equal. Negate that. Add to that 50 times root 2. Okay. I'm slow on this. Sorry about that. Times the 4.24. That was the time. Okay. And then add to that 3. All right. Looks like it'll go up to about 14.8 feet. Okay. Now maybe if Kyle were playing the fielder out there, he probably could jump that high and grab that ball, but most fielders aren't as good as catchers, are they? So
No, sir. That's routine for us.
Yeah, right, of course. Okay. As you get those foul balls behind the home plate, right? Okay.
Correct.
Okay. All right. So we got that it did clear the fence, so it must have been Kyle at the plate. Okay. Now they say, oh yeah, they rounded. I said 14.8. They rounded to 15. Okay. And they said 4.24 seconds. So got it. The ball clears the 10-foot fence for a home run. Oh, Kyle, I forgot to tell you that was past the foul pole. So never mind. Okay. Okay. Enough of that. Now, that finishes. That's the last problem in 12.3. Always take a look at the concept check. That's a good thing to do. Review, make sure you have the concepts right, then proceed doing the problems. Okay? Homework exercises then would be any of the odds 3 through 9. They're all at Calc Chat. 3's at Calc View. Then 11 through 19, they're all at Calc Chat. 15's at Calc View. 21 to 25, they're all at Calc Chat. 21's at Calc View. And then projectile motion problems, 27 through 39, a whole passel of those there. They're all at Calc Chat. Then number 41 should be at Calc Chat, another projectile motion problem. Then we have another catcher type thing, shot put throws, only you're throwing the second base. So 43, that should be at Calc Chat. 45 should be at Calc Chat. Either 47 or 49 should be at Calc Chat. 51 should be at Calc Chat. And any of the odds 53 through 59 should be at Calc Chat. And then you got 2 true false, 61 or 63. They should both be at Calc Chat. Any questions on 12.3? Oh, wait, let's watch them do the problem. I'm sorry, I forgot that. Given an initial height of 3, initial velocity of 100, and the angle of motion would be 45 degrees. That will be your velocity angle. Okay, so using theorem 12.3, which we just did, G is 32 feet per second, which is 32 feet per second squared, because we're in the U.S. customary system here, not SI system. The R would be 100 times the cosine of pi force Ti. That's your velocity times T, V0T in the X direction. 3 in the Y direction, plus 100 times the sine of pi force T. Why they went, they gave you it in degrees, and now they're dealing with radians. I don't know why they did that, but they did. 100 times sine of pi force T minus 16t squared. That was your 1/2 of 32. They went straight to that. And those are all in the j direction. Okay? This thing gives you the cosine of pi fourths, or 45 degrees, is root 2 over 2. So this becomes 50 root 2 t I. And then here you have your 3. And the sine of 45, or pi fourths, is also root 2 over 2. So this will give you 50 root 2t. So any angle other than 45, this number and this number will be different. Only at 45 are those the same. Okay? Root 2t minus your 16t squared. Okay? In the j direction. So there's your displacement vector anytime t. Okay? Now, the velocity vector is your first derivative of your displacement vector. Now, don't know exactly why they're doing this, but it is true. And that would be 50 times root 2 I. I'm sorry, I'm running out of energy. Hold on. I'm really getting tired of this anemia. Okay. 50 times root 2 I. That's just taking the first derivative of that. It's just a constant. Plus, the 3 goes away, 50 root 2, that's a constant, minus 32t j. So there's your velocity vector at any time t. Okay? Now, the maximum height occurs when your y component of your velocity is 0. Okay? So that's what they do next. It's when y prime is equal to 0. They didn't mention y prime before, but here they did. It's the vertical component of your displacement vector when that is equal to 0. Set it equal to 0 and you get this, and the thing keep popping up whenever they want to. 50 divided by 32 is 25 over 16 times root 2, and that gives you about 2.21 seconds. Now, I didn't remember that being that. I just want to check their number there. Sort of suspicious by nature. Not really, but when it comes to calculus, I can get that way. Okay, what were we doing? 25 divided by 16 times root 2 equal, yeah, 2.21. Okay, I just rounded to 2.2, but it is 2. I mean, if you take it an extra digit, it will be a 2.21. Actually, I used the whole number. They didn't, but that's okay. All right. So the maximum height will be reached when the ball has been up that long. Well, the height was your j component of your displacement vector. So we take that time that we had here. Now they go back and use the radical form. Don't know why, but they do. Actually, there is a good reason why. The root 2's become 2, okay? And this root 2 squared becomes 2. So it makes for a lot easier calculation than maybe what I did, okay? And you can also divide out, make this 8 down here and that a 25 up here. So you have 25 squared times 2 divided by 8, and this would be, yeah. Okay, that's just a thing. That gives you 649 over 8. Yeah, I was going to do those fractions like that. And that gives you about 81 feet. Okay, and that is not using any round off at all. They're not using this round off seconds here. They're using the exact value, which will give you a more precise answer. So I got 80, they got 81. Theirs is more precise than mine. And that would be approximately the height. Okay? Maximum height. So when it's 300 feet away, we go back to our initial velocity, initial displacement vector, and 300 feet is a displacement, so that was your 50 times root 2t. Solve that for t, and you get your 6 over root 2, okay, which would be, well, works out the same way, and it gives you 4.24 seconds. Now, interesting here, they do use that one, I think. No, they use this one. They use your absolute, your precise value, your exact value, 3 root 2, plugging that in again in your y component to see how high. This is to get you out there to 300 feet horizontally. How high is it going to be when you get that far out? What is your vertical component? 3 plus 25 root 2 times 3 times root 2 minus 16 times 3 times root 2 squared. And if you combine your root 2's, that gives you a 2. This gives you a 2. That gives you a 9. That gives you a 16 minus 16. So do all the calculations there. And I guess they add the first two together and subtract the last one from it. They didn't show how they got the 288 or the 303, but we'll assume that's true. Yeah, we can check this one. This one's pretty easy. That would be 50 times 3 would be 150 times 2 would be 300 plus 3 would be 303. So that's where they got that. And this would be 16 times 9 times 2. Okay, whatever that, I bet you it comes out 288. And that gives you 15 feet on the nose, and that's the height at approximately 4.24 seconds. Okay, at exactly that many seconds. Not approximate, exactly that many, but that's approximately that many. Therefore, it will clear the 10-foot fence for a home run. Even pushing off the wall and everything else, I don't think that guy could climb up that much. If he could, sign him up for basketball, because he could dunk the ball really easily. Okay, so maybe he'll play both sports. All right, and that did end the slideshow. So let's move on from there. Discard the stuff from there. And what do we got about? Well, we got plenty of time, I think. So let's end this PowerPoint and go to, I always put those things right in the way. 12.4. Okay, I'll make sure I had the right one loaded. Okay, now I've got to do all this adjusting again. So let me move. You can't see it, but that taskbar is smack in my way, and we'll go from current slide. Okay, here is 12.4. We're still in chapter 12, vector value functions. Very athletic in this chapter, aren't they? They got a Navy quarterback here and I can't tell what school she's from, but a shot putter there, a woman shot putter there. And the rest of it looks like just driving on a road and air traffic controller and a spiral staircase or something like that. But 2 out of 5 are sports. So let's do 12.4, tangent vectors and normal vectors. Okay, our objective here is to find the unit tangent vector and a principal unit normal vector at a point on a space curve. So 12.3 was kind of stuck in there. Velocities and accelerations are important things to do. Now we're going back to what we're doing in 12.2, your space curves. Now notice we're no longer in the plane. Okay, one of the reasons for that, you can't have a unit normal vector described in just planar terms because it's always perpendicular to your your displacement and your velocity vectors. So therefore you have to be in 3 space or in space curves in order to talk about unit normal vectors. You can talk about unit tangent vectors in 2 space, but principal unit normal vectors you need to be in 3. So we'll find the tangential and normal components of acceleration if we get that far. The velocity vector points in the direction of motion. In space, in plane, wherever you are, it points in the direction of motion. That observation leads to the next definition, which applies to any smooth curve. Now notice smooth curve. You can't have any cusp, corners, or things like this. It has to be nice, rounded, smooth curve. Okay, not just to those that for which the parameter represents time. So now we're no longer dealing with just velocities and accelerations. You're talking about any kind of curve with any kind of independent variable. It doesn't have to be time. So here's the definition of your unit tangent vector. Let C be a smooth curve represented by some vector r on an open interval I. Now that open interval I is covering your t variables. Remember that t variable is not necessarily time anymore, whatever that variable is. And I is the interval of those t values. The unit tangent vector, and they name that capital T of little t. The little t is your parametric variable. Capital T is your unit tangent vector. Now they bold it, capitalize it. I can't bold, so I capitalize it, but I put a house cop on it because it's a unit vector. At any time t is defined this way. Now number 1, your first derivative is your velocity vector. It's in the direction of your motion. So it's tangent to that curve, always. Well, since it's tangent to the curve in the direction of motion, that's the same direction as the unit tangent vector. So how do we make that velocity vector, though it doesn't have to be velocity anymore, but using that, into a unit vector? Divide by its magnitude. So now that we're talking about any kind of curves here, this isn't necessarily velocity, so take your displacement vector, the first root of your displacement vector, and divide by the magnitude of the first derivative of your displacement vector, and that gives you your unit tangent vector. Now, of course, the first derivative of the displacement vector cannot be 0. If it were 0, it doesn't have a unit normal vector because it has no magnitude. So how could it have a length of 1? So to be a unit vector, it has to have a non-zero first derivative. Okay? We know that a curve is smooth on an interval when r prime is continuous and non-zero on that interval. When the r prime is continuous and non-zero on that. So the smoothness is sufficient to guarantee that a curve has a unit tangent vector. If it does not have a 0 first derivative vector, then it has a unit tangent vector. All right, so here we have, find the unit tangent vector to the curve given by, now this is a plane curve. Remember, you can have unit tangent vectors on plane curves. That's perfectly fine. okay, to this curve, r of t is equal to ti plus t squared j. We're going to find it when t is equal to 1, but we find it when t is generic to begin with, and then plug in 1. Don't plug in 1 now, you'll get a 0 when you take a derivative. So what we do is r prime of t is equal to, anyone tell me? First derivative of t is 1. So that would just be I. And the first derivative of t squared is 2t j. Okay? That's at any time t for that displacement vector. Well, when t is equal to 1, r prime, well, let's not do that yet. Okay? Yeah, let's go on and do it. Wait, let me think. Let's go on and do its magnitude first. R prime of t magnitude would be, anyone know that one? Square root of this squared plus that squared. Okay. That would be its magnitude at any time t. Now, we need to calculate that. Okay, they didn't ask for the unit tangent vector any time t. That would just be the ratio of those. But they're asking for t is equal to 1. So let's do r of 1. That would be I plus 2j. And the magnitude, r prime. Okay, magnitude of r prime of 1 would be the square root of 1 plus 4 would be 5, which is what you get if you plug in t equal 1 here. Okay, so what is your unit tangent vector when t is equal to 1? Unit tangent vector, I put a housetop over it because it is a unit vector. That helps me remember it's a unit vector. At 1, they didn't ask for any time. If they wanted any time, you just take this thing, divide it by that thing. But at 1, it would be I over, goodness gracious, pen is doing strange thing. Over, goodness, the pen is nuts today. Okay. Over root 5 plus, this pen is nuts, 2, I don't know what's gotten into it, over root 5 j. Whew, it's like pulling teeth. Okay, now real easy to check to see if that is indeed a unit vector. 1 over root 5 squared is 1/5 plus 2 over root 5 squared would be 4/5. 1/5 plus 4/5 is 1. Yep, that's a unit vector, and that is the direction. So that is the unit vector, unit tangent vector at t equal 1. Now let's see how the book did it, or the PowerPoint did it. Okay, they took the derivative first, exactly what we got. Okay, then the unit tangent vector was the derivative r prime divided by magnitude of r prime. Well, they haven't figured out what magnitude of r prime yet, is it? And here they did it. Just like we said, it's the square root of 1 plus 4t squared. Okay, so that is the 1 over this, and then multiplied by r prime, which is that. And then plugging in when t is equal to 1, that's 1 over root 5 times I plus 2j, which, oh, it sort of drives me nuts. In other places, they insist on having the coefficients with each thing, and here they don't, so it doesn't matter. Okay, so when t is equal to 1, there would be your unit tangent vector going up at a right 1 up to ratio, but with the square root of 5 as a coefficient in it. So, yeah, that looks about right. All right, any questions on example 1? Okay, I'm going to have to get some more soda, sorry. I think part of this tiredness is the fact I had basically no lunch, so my blood sugar is probably pretty low too, so that will not be too bad to be drinking this soda. Okay, now the tangent line to a curve at a point on the at a point is the line that passes through the point and is parallel to the unit tangent vector. Okay, that sort of makes sense. Tangent line to a curve is a point at a point is the line that passes through the point. Got to do that, otherwise it's not tangent at that point, and is parallel to the unit tangent vector, of course. Okay, now I think I would have phrased that is along the unit tangent vector, because to say parallel, well, that could be somewhere like this. Well, it's not. Well, I guess the unit tangent vector doesn't have to be on the curve. Okay, so that's what they're saying. So anyway, in example 2, a unit tangent vector is used to find the tangent line at a point on a helix. So let's do example 2. Find the unit tangent vector as a function of time, and then find the set of parametric equations for the tangent line to the helix given by r of t is equal to 2 cosine t I plus 2 sine t j plus tk. At this point, root 2 pi fourths. Okay? Now, hold on a moment here. I want to make sure that this point is on that line. Okay, where in the world is my pen? There it is. This point is on that vector. Otherwise, it doesn't make any sense. So the t here obviously is pi fourths, because that's the coefficient, the component of your k vector. Okay, pi fourths. So cosine of pi fourths is root 2 over 2 times 2 would just be root 2. Sine of root 2 over 2, sine of pi fourths is root 2 over 2 times 2 would just be root 2. So sure enough, these components do match this displacement vector. That point is on it. Okay, so that was just something I always like to do first. Okay, what do we have to do next to find t of t? Take a derivative. R prime of t is equal to minus 2 sine t I plus 2 cosine t j plus k. Okay, there's your r prime of t. Now, to get the unit tangent vector, we're going to need to divide by the magnitude of r prime of t. And that would be the square root of Negative 2 squared would be 4 times sine squared of t plus 2 squared times cosine squared of t. That would be 4 cosine squared of t plus 1 squared is 1. Okay? Well, guess what, folks? We know what signs we can, in the first two terms here, factor out of 4. Okay? And that leaves us as sine squared t plus cosine squared t. Okay? Then we have a plus 1 there for some reason. That's from here. Okay? Well, what's sine squared t plus cosine squared t? One. So this will be 4 plus 1. This is root 5. It seems like we had that before, didn't it? Okay? Different context. So there's the magnitude of that. Okay? So the unit tangent vector would be the unit tangent vector as a function of time. Well, I say time. As a function of t is then this thing divided by root 5. So it's minus 2. I go to write root 5 over 5. Okay, I multiply numerator and the denominator by root 5. Minus 2 root 5 over 5 times the sine of t in the I direction. Plus 2 root 5 over 5 times the cosine of t j. Okay, I don't know what that noise was. Does anyone? While I'm investigating, I'm going to get another swig. Okay, sorry about that. Okay, plus root 5 over 5. Okay, I don't know if they rationalized the denominators or not. Let's see if they did. Oh, wait. I'm sorry, I got carried away here. All I looked at was find t of t and then find the set of parametric equations. I hadn't gotten to that part. For the tangent line to the given helix, blah, blah, blah. Okay, we found t of t. That we were supposed to do. Let's see if we agree with them. They pulled the 1 over root 5 out front, which is perfectly fine. So they just did it this way. 1 over root 5, which is a lot shorter to write. I thought they wanted to do it. Times negative 2 sine t I plus 2. Yeah, get out of there. This is so aggravating. Okay. Plus 2 cosine t j. I'll put parentheses again. Plus k. Okay. All right, let me make sure nobody else is waiting to come in. I don't think they are. No. Got the same 5 we had originally. Okay, 1 over root 5 times minus 2 sine ti plus 2 cosine tj plus k. Got it. Okay, they didn't multiply through by the root 5 over 5. Okay, now, so we've done the first part. That's finding the unit tangent vector right there. Then find a set of parametric equations for the tangent line to the helix given by that expression we've already used at the point root 2, 4, which we've already confirmed is on that helix. Okay. So our set of parametric equations are going to be something like x is equal to something, y is equal to something, and functions of t. Now, and our t, remember, is pi force. Okay, we got that from this having to be that. Okay, that's what t is. Okay. Oh, okay. Okay, as I've already said, t is pi force. So what they're doing now is taking this expression and plugging t equal pi force in. Okay, so if I could get my pen to show back up, it was right there. There it is. Okay, so unit tangent vector at pi force, because that is your t value, is equal to 1 over root 5. Now, sine of pi force is root 2 over 2. So this is going to be minus root 2 I. This is root 2 over 2. Cosine of pi force is root 2 over 2. So this is plus root 2j and k plus k. Okay, because there is no t dependence there. Okay, now let's just for a moment pause and say, is that still a unit vector? It better be. Well, negative root 2 over 5 squared would be 2/5 plus 2/5 plus 1/5. 2/5 plus 2/5 is 4/5 plus 1/5 is 5/5. Yes, that's still a unit vector. So there's your unit tangent vector at pi force. Okay. Now, they didn't specifically ask for that, but the direction numbers, if you remember back when we did I'm trying to think of parametric equations, the direction numbers were multiples of those coefficients. Now we can leave off the 1 over root 5 and just use minus root 2. So your A is minus root 2, B is root 2, and C is 1. You don't have to have the over root 5 in there. You could, they would be good numbers too. Then the point, imaginary point somewhere, well, no, not imaginary point, the point of intersection, they're calling this, if I could get my pen to show up again, there it is, okay? They're calling this x1, y1, z1. That's the point on the curve, okay? Then the parametric equations would be, like I said, it's going to be x. Okay, now their parameter before they were using t. Since we've already used t's here, just to keep from confusing them, any letter will do. They're using s. So x is equal to your x1, which is root 2, then your ax, so that would be minus root 2s, y is equal to root 2, that's from here, there's so many root 2's in here, plus root 2s, and z is equal to pi fourths plus s. Okay, and that would be your tangent line. Now I know that doesn't seem like a tangent line, but indeed it is. Okay, you think of things like that as being a single equation. In 3 space you need 3 equations for a line. Planes will be a single equation. You know, other things, lines will be component by component. Okay, now how are we doing? We go to 155. Okay, so we've got, okay, let's clear my scratch here if I can. I think we've done everything they asked for. Okay, and let's see how they did it. The derivative of r of t is r prime of t, which is minus 2 sine ti plus 2 cosine ti plus k, just like we got, which implies that r prime, the magnitude of r prime of t is the square root of 4 sine squared t plus 4 cosine squared t plus 1, and because sine squared t plus cosine squared t is always 1, factor out of 4 times 1 is 4 plus 1 is 5, so this is root 5. Therefore the unit tangent vector is this vector here divided by root 5, which is 1 over root 5, there that is, times minus 2 sine ti plus 2 cosine tj plus k. Now, at the point root 2 pi fourths, the t, because now this is the unit tangent vector, it's not the original, but if you go back to the original vector, it was tk, so that component here must be t. Okay, so when t is equal to pi fourths, the unit tangent vector at that point would be 1 over root 5 times, because sine of pi fourths is square root of 2 over 2, put that instead of sine, that instead of cosine, and just leave that alone. That would be minus 2 root 2 over 2i plus root 2 root 2 over ij plus k. The 2's will go out, and that leaves you just root 2's in the numerator, so that would be negative, that would be 1 over root 5 times negative root 2i plus root 2j plus k. That's your unit tangent vector at that value, t equal pi fourths. Now, the line, the tangent line to the curve at that point has to be in the same direction, and these ratios, these are your direction numbers. You could have carried along the over root 5, but all of them would have had that, so why carry around an extra thing? Just a ratio of those, minus root 2, 1. Okay, so those are called your direction numbers. Minus root 2 for A, the x component, root 2 for B, the y component, and 1 for C, the z component. And that point where it touches the line, this is a point from the line, is root 2 pi fourths. So you can obtain the parametric equations from x equal x1 plus as, they're using s as the parameter now, y is equal to x2, root 2 again, plus bs, let's not use that too much, and z would be y3, y1, I'm sorry, z1, which is pi fourths times plus cs. Okay, so this one would be root 2 minus root 2s. That's your x. Root 2 minus root 2x. Your y would be root 2 plus root 2s. There it is. And z would be pi fourths plus s. Got it. Okay. And those are your parametric equations representing the x, y, z components of your tangent line to that point of that curve. All right. Now here, goodness, that doesn't look like a helix at all. Yeah, it is. Okay, I see it now. Okay. It's a circular base here, but it's leaving and going up at pi fourths here and pi halves here and 3/4, yeah, all like that. So it's going up here and it's going around and around. This is what threw me. That's on the back side and this is on the front side, and it keeps going up and up. Tracing, basically, imagine a tin can that you slice like that, you know, but this just keeps going up. Infinite tin can from the bottom. Okay, and at this point here, the unit tangent vector, the tangent line at that point right there would then be here, which would be described by those parametric equations we just had. Okay, now in that example, there are infinitely many vectors that are orthogonal to the tangent vector. Okay, t of t. Let's go back and look. Yeah, here's the tangent line here, right here, and you could do a perpendicular here. You could do perpendicular in any direction. You can go all the way around that tangent line drawing perpendicular lines. Okay. Now we're going to look for a perpendicular line to that, an orthogonal line to that, but we're going to want it very special. One of those is the vector t prime of t. Okay. Now, it may not be intuitively obvious to you that the first derivative of the unit tangent vector is perpendicular to the unit tangent, or orthogonal to the unit tangent vector. But here's why. It follows the property that t dot t is equal to the magnitude of t squared, but because that's a unit vector, that's 1 squared. That's 1. Now, because of that, now this is a little bizarre here, but it's true. If you take, they're skipping so many steps here, it's pathetic. Okay, if you took a derivative of this expression here, I can't get my cursor to come back, there it is. Take a derivative of this expression here and take a derivative of that, the derivative of 1 is 0. Well, what is the derivative of this? It's t dotted with t prime of t plus t dotted with t prime of t. So it's 2 times t dotted with t prime of t. That's equal to 0. Divide out the 2. Well, here's t dotted with t prime. It's got to be 0. That means they're orthogonal with each other. So that's where that comes from. Strange but true. Now, if you normalize that vector, meaning make it a unit vector, you can obtain a very special vector called the principal unit normal vector. Now, normal means perpendicular, just like orthogonal means perpendicular, as the perpendicular means perpendicular. But this time we're talking at the normal vector or perpendicular vector. Okay? And here's how you do it. The definition of the principal unit normal vector. If C is a smooth curve represented by R on an open interval I, just like we've done before, I is the interval of your T parameter here, the values that T can take on. Now, if T prime, that's the first derivative of the unit tangent vector, is not equal to 0, okay? It can't be equal to 0, but if it's not, then the principal unit normal vector is defined as capital N of T, and that's also a normal unit vector, is T prime. Now remember, T is a unit vector. T prime is not necessarily a unit vector. In fact, most of the time is not. I guess there are some occasions when it would be, but most of the time it's not. So you take your first derivative of the unit normal vector, unit tangent vector, and divide by the magnitude of that unit tangent vector, and that gives you your unit normal vector. Okay. Now, yuck, we have just gone over 2 minutes. We didn't get to do example 3. All right, sorry about that, folks. That is it for the course. Okay, sorry we didn't get to go into any more into finding a principal unit normal vector, but you know how to do it now. And then the next part of this section was going to break down the acceleration vector, going back to accelerations then, into a tangential and normal components, and we're not going to get there. Sorry about that. Homework exercises here, if you choose to do them, would involve any of the odds 3 through 7. They're all at Calc Chat. 5's at Calc View. Any of the odds 9 through 13, they're all at Calc Chat. 9's at Calc View. And then you could try doing some of the odds 15 through 19. They're all at Calc Chat. 15's at Calc View. We talked about how to do them. We just didn't get a chance to do an example. Okay, now what does that mean? Your test will be a pretty short test. Sorry about that. My guess is only about 6 or 7 questions. Now there'll be 10 questions on your test because it's already made out. I was hoping we got farther than we did. But you'll only have to do certain ones of them. So if you don't mind, let me first get out of this. Okay. And what I'm going to do is go to, wait, I may have it open here. Yeah, here it is. It's going to take me a little while to find it. Here it is. Okay. Let's see. Let me just take a look at what I'm calling test 3 here. No, that's not it. We didn't get nearly as far here as I had hoped we would, but we were almost doomed from the beginning. I believe this is it. Okay. All right. Now, obviously, isn't test 2 anymore, but okay. This is what we've been covering in this chapter. Now, I've got to move y'all out of the way in order to advance this. So I'm going to move y'all over here. Okay. I know you can do questions 1, 2, 3, 4, 5, 6, 7 you can do. I think you can do 8. Okay. I see a typo here. That's per second, not slash second. Okay. I think I started to put slash and then put, I don't know what. I think you can do 9. Because we did one like that in class. Okay. We didn't do arc length. Arc length was in 12.5, I believe. Yes. So we didn't do arc length. So number 10 will be optional. Okay. But I think you can do the first 9. Okay. So if you do number 10 and get it right, you get bonus points. If you try number 10 and get it wrong, it doesn't hurt you. If you leave number 10 blank, it doesn't hurt you. So you're only going to be tested on the first 9 questions here. And the 10th one, if you want to try it, you can. If you get it right, you get a bonus point. It cannot hurt you. It will not detract anything from the score of the first 9, but it could give you a better score. Okay? So, how's that? And I'll try to get this corrected to 130 feet per second rather than slasher second. So that's what your test is going to look like. Now, thing is, I can't give it to you now because this is in WordPerfect format, and I don't think any of you probably can read WordPerfect files. So what I've got to do this afternoon, after 4 probably, is go downstairs and do a Adobe scan of this test and then send it to you as an Adobe file, because I don't think any of you can read WordPerfect. Can you? Okay. All right. Any questions? All right. For those who came in a little later, let me remind you of what we said earlier. Please do the student course evaluations. Okay, they're out there now. They didn't get them out there until either the week before Thanksgiving or the week of Thanksgiving. So you haven't had much time to see them, but please do them. If you were in a first mini-term course, please do the first mini-term evaluation as well. Okay, I know that was a while back, 6 weeks or so, but try to remember enough about it, maybe 7 weeks by now, maybe close to 8 weeks by now, but try to remember that and do that one as well. Also, some of you are graduating this term. Am I not correct? I know Kira is, or any of the others. Laron, are you graduating this term? Jemanuel, I think you are. Yeah.
No, sir. I have to finish 2 more chemistry.
Okay. Okay. How about Jemanuel? Are you graduating this term?
No, I'm graduating next semester.
Next. That's right. I knew that because I did that letter for you, or email for you. But I know Jesus and I want to say Thomas. Is that his name? No, James. Okay. James are graduating, as is Kara. If y'all are graduating, please get your test in as soon as you can, because I don't know when your grades are due in, but it's before everybody else. So don't procrastinate. Get me your everything in. Now, if any of you have not turned in your research paper, and I think that may be a few of you, I need it today. Today is the last day of class, and anything I get after today, like tomorrow, Friday, Saturday, whatever, you'll be losing points. So please get them in today, okay, if you haven't turned it in already. If you haven't turned in your earlier tests, get those to me as soon as you can, okay? And then this final when I finally get the Chapter 12 test, when I send it to you, try to get it back to me. For those who are graduating, get it back to me as soon as possible. For the rest of you, technically, I think it would have been Monday of next week. I'm not going to hold you to that. Wednesday will be fine. Thursday will be fine. Noon on Friday is the latest that I want to have any of these things coming in. Okay? Please get them to me before noon on Friday so I have a chance to grade them, get them in the books, get them in Blackboard, and get the grades averaged before next week. I think the grades are due in by noon on Tuesday for non-graduating students. For graduating students, I think they need to be there sooner than that, because y'all graduate next Friday, don't you? Kira? Okay, I don't know if she's still here or not. So anyway, so I know that I need them earlier than Tuesday week. So please, well, earlier than next Friday noon. So get them to me as soon as you can. Any questions? I'm going to stop sharing here. Okay. Any other questions? And as I was telling the folks earlier, this is my last Cal 3 class maybe that I'll ever teach, but it's been a good one. I appreciate you as students. You helped me go out with a good group. So anyway, take care.
I appreciate you too. Thank you for everything you've done.
Well, thank you so much, and take care. Please be careful. The virus is almost out of control right now. You don't want to catch it, and you don't want to recatch it either, because the immunity is not permanent. Okay, so be careful. Always be careful. Take care, folks. We'll see you sometime. If you ever need to get in touch with me, my email address will still be good through up to the beginning of February. If you need to get in touch with me after that, you'll need to get in touch with me before the end of January so I can give you my new email address. Okay? Take care. Bye-bye.